Welcome to the August 17th OMR Architecture Meeting. Today we have a continuation of the topic that we began discussing last time. So Mark was giving us an update on JitBuilder 2, and he'll take us through the next phase of that in his presentation today. So turn it over to Mark.
Great, thanks, Daryl. All right. I'll assume everyone can hear me, hopefully. Right, so last week I talked about a number of things in the update on JitBuilder 2, but there were some topics that I didn't get a chance to go into. In fact, I hadn't had a chance to create slides for them yet, so I've now had an extra month to create some slides, so I've got a few extra topics to go into here today. Just as a reminder, I'll pop this slide up again on the goals for JB2, JitBuilder 2, are really around improving the usability of the library and especially on the topic of extensibility, and that's one of the topics that I've got on the agenda for today's presentation. And I guess one of the other things to point out, which I think I forgot to mention last week, is that our last presentation was that really the state of things, it's really building out a framework for building compilers. It's not really a compiler itself, although there is a path to using the JitBuilder API to actually generate code, so it can do some interesting things right now, but it's not really a fully fledged compiler per se. So just keep that in mind when you're seeing all of this stuff. So I wanted to start off by, since the last presentation basically went right to the end of the meeting time and there wasn't really any time for questions, I thought I would give a pause at the very beginning to see if anybody had any outstanding questions that they didn't get a chance to ask last time. So this will be that time to pause. There's a couple people in the room who I'm looking at. They're not really looking like they have questions, but they're chuckling. Nobody's asking questions. Does anybody on the call have any questions? All right, no worries. I'm perfectly happy for this to be a short section. The other three topics that I had, as I realized after doing the talk, actually while I was starting to create slides for this presentation, I realized that I'd never actually shown any IL printout from the compiler framework last time. I'd only ever talked about the code that you write when you're writing a compiler. So I thought I'd go through an example output for one particular, it's actually one of the test functions that runs as part of the base extension. And I'll just show you kind of what that looks like. It's not complete, but it's a fairly, it showcases some of the features of the compiler framework. And the third topic was memory and allocators. Always a topic of great interest, I guess. Very important topic for a compiler, especially a dynamic compiler like a JIT compiler. And then the last topic is extensibility, so I wanted to go into some of the details for how some of the dynamic extensibility mechanisms work in JB2. All right, so let's dive in, because it's probably going to be another hour-and-a-half meeting, or could be. Anyway, so I'm just going to put up this IL. This is basically something that you can get it to print out automatically from running a particular compile. It can print out the state of the IL. This isn't perfect right now. There are some changes that I still need to make to it, but I can take you through and show you kind of the flavors for some of the stuff is. Now there's 5 slides here, so don't think this is everything, but this is where it starts off. So basically it uses square brackets as kind of a delimiter, so you can pop back and forth between beginning and end of a lot of different things and understand where they apply. A compilation has actually, one of the things that I've done in the last month is recently I just took all of the basic IL that gets created in the compiler and put it under an object called IR. So there's now an IR object that hangs off of the compilation, and it holds on to all of the stuff that I'm going to talk about on these next few slides. So it's kind of a one-stop shop for the structure of the IR, but it doesn't actually print out as part of the representation right now. Anyway, there are 3 types of dictionaries, interestingly, which are associated with a JitBuilder function in this case. One of them is a type dictionary, and it's basically responsible for having all of the types that are being referenced in this compile unit. You can see there's a linked dictionary here. So this is type dictionary T1. Everything gets an identifier. So this is the number 1 type dictionary. It has a linked dictionary, basically a parent dictionary, which is T0. T0 is the sort of a type dictionary that's associated with the compiler object. So the compiler object gets T0. If you have types that you want every compilation to be able to see, you can define them there. In fact, that's where these primitive types come, because they're created by the base extension, which you can't tell that right now from the output, so I need to change that. But essentially, each one of these lines shows shows a type that's been created inside this type dictionary, and they are also given identifiers. The lowercase t is an identifier for types, uppercase T for the type dictionary. So type 0 is a special thing called no type. It's kind of like void, and then so the usual sort of primitive types that you had access to in the JitBuilder API, and they're all tagged as primitive types, so they all print out and you can tell what they are. These ones are fairly obvious. One thing to note for JitBuilder users is I've changed float and double into float 32 and float 64 just for consistency with the integer types, and to provide a more reasonable way of referencing other sized floats should that become of interest.
Is dictionary T0, capital T0,
yep,
described this way as well?
No, it's not right now. So the T0 does not come out as part of this this output right now, but it could. I mean, T1 was printed by calling a function on the type dictionary to print itself out to the log. So in principle, you can print out T0. I haven't worked out all of the sort of logging options that are needed here, but certainly you could get this same output from T0. And in fact, like I said, T1 actually inherits these types from T0 in this case.
So like in this case, you're saying that type lowercase T4
yep,
is it's essentially an int64.
Yep. Yep. It represents, its name is actually int64, and it's got 64 bits, and it's an integer, but it's the name. So it represents 64-bit integers.
So what is it getting from the dictionary T0 here then?
There is also a type T4 in T0 that in the type dictionary 0 that is the 64-bit int64. So it just inherits these types. So basically, what happened in this particular case is those extensions can come along, and if you have something like a primitive type where you don't have to create different versions of it, like pointer to pointer to pointer to int64 might not be a type that you'd use everywhere, but if you had a compilation unit where you needed that type, you could create it, and it would be in that type dictionary. Okay. In the case of the primitive types, they're all the same, so the extension basically creates it and stores it into the compiler's type dictionary, and then when you create a compilation, that type dictionary for that compilation basically inherits those primitive types. And so that's what this is showing, although it doesn't actually show the inheritance aspect. So need to figure out this logging a little bit better, but anyway, that's basically it. Okay, so in addition to a type dictionary, there's a symbol dictionary, which holds the symbols that are defined within the compilation unit. It also has a linked, and same mechanism here. Capital is the dictionary, lowercase is the symbols. There's a linked S0, which is the compiler's symbol dictionary. So if you had global symbols that the compiler wanted to create or that the extensions wanted to add to, you could have them there, and they get inherited. In this particular compilation, which I should have actually shown the code that it actually does, this function is a test function for a for loop. So it has a for loop inside it and parameters so that you can change the initial bump and final values of the loop, so that it will change how many times the loop executes, and it can test whether the iteration actually happens. So it has those 3 parameters you can see here. S1 is like all of these symbols have an underscore T, which tells you what type that parameter is. So you get to go back to the type dictionary, which is awkward here, but I can, T3 is int32. So these are all 32-bit integers. Additionally, the I for the iteration count of the loop is also an int32, and this counter guy is for some reason, he's a 64-bit integer because he's just basically accumulating a count of the inside the loop. So if you iterate a lot of times, you can't actually blow up the 32-bit above 32-bit. So it's just created it as a 64-bit. There's also a literal dictionary to hold literals. So constants are represented a little bit differently than in JitBuilder. You have to actually call out your literals and create them. So here there's a 64-bit integer, 64-bit integer 0 for the value 0, one for the integer 1, and they're also named and then can be referenced in later on in the IL. And again, same basic idea, right? There's a capital L for dictionaries, there's a lowercase l for actual literals. And then we can get into what are we actually compiling. So this provides details of the compile unit. In this case, it's a function. Its name is that god-awful thing, which actually gets constructed because there's a whole bunch of tests that test different types being used for loops. All of them are supposed to be blocked except for this one, which uses 32 bits, because it's the only one that's actually supported by JitBuilder, really. Anyway, so it has this naming scheme. It's like initial, final, bump, and the iteration counter types. So all of those types can be set to different types, and then it creates a for loop function for it.
That's just a naming convention that you choose.
Yeah,
it's not like a Java signature.
Yes, exactly. It's not a signature at all. This origin is like the creation location for, so this is the origin, the spot in base test, which is the name of the file that has all the tests for the base extension in it. So line 1074, and it's using gtest, so the thing gets embedded in a function called test body. It has a return type of T4, which was our 64-bit integer guy, right? So basically, it's going to return the counter because it's a 64-bit integer. And then just vestigial, this probably doesn't need to be here, but it's this part of the context for the function. So it lists, again, the parameters and the names, as well as the local variables and the names that are available. And then the last one is this entry point, which is how you get to where the code is, basically. And there can be multiple entry points, but JitBuilder, not JitBuilder 2, JitBuilder itself only supports a single entry point for functions. So right now you can only have a single entry point, but in principle, you could have multiple entry point compile units. And so B1 is how you reference builders with a capital B. So what do builders look like? So here's the entry builder. So it's a capital B1. Again, they're numbered. It has a name. You can give builders a name. You don't have to give them names, but it has a name if you wanted to. Builders can have parents, so there's a tree structure of builders within the function, and it's also got a scope. I talked about scopes in the last meeting, which basically represents a region of code. So this builder is a part of this scope 1. I don't know why I need to find a different sort of name for this, but S is already taken for symbol, so I made it a little bit more verbose, which is basically the scope for the entire function. So we're not really breaking things down. B1 has several children builders, and that comes out as we'll see later what's inside this builder. We'll be able to see what these builders are. It is not a bound builder, which means the control in and out of this builder is not determined by some operation somewhere, that somebody branches to it, in essence. It's not a target of a branch. And then the operations are listed here. We have this nice tag, which makes them sort of easily to identify where these operations are and in which builder they originate, so you can find things fairly easily. And then sort of familiar kind of 3-address type form where you've got values, which are V with an ID associated with them, again, underscore with the type that they have. So all of the IL is typed. Sorry, all of the values that you're working with are typed, but the operations themselves, the actions are not. In JitBuilder, we used to have things like constant 8, constant 16, constant 32, blah, blah, blah. Now there's only a constant thing, which basically tells you to load one of the literals. So it just references a literal, which is L1. And as a reminder, it tells you that that's in 64 and a 0. So you know that this is the 64-bit integer 0, constant being loaded into V0. And then it's just a sequence of operations. So it does a store with a symbol. And again, it reminds you of what it's called, so you can kind of follow along with what it's actually doing, right? It's storing 0 into counter. Then it loads the parameters so that it gets the initial, the final, and the bump for the for loop. The interesting one is 06 here, which is a for loop up operation, which basically uses this. It says I'm going to use the symbol I as an iteration variable, and then it's going to loop from V1 to V2 by V3, right? So initial to final by bump. And then the actual code for the for loop is specified by the body. So the code that's inside every iteration of the loop is B2, builder B2. And then if somebody needs to break out of the loop, they can branch go to the loop break builder B3.
question.
Yes.
I may have missed this when you first started going through the example.
Okay.
Is this what someone would write, or is this the output?
No, this is an output. This is a logging output, basically.
Okay, so it's not. This is not how someone would describe it.
No, no. This is just a textual form to help people look at what the IL is.
Got it. Yeah.
Right. It's kind of like a Testarossa lump, the tree dump, the trees. All right, B2 and B3 and B4 are examples of bound builders. And I mentioned B1 is not bound, so B2, B3, and B4 are bound because the control in and out of those builders is determined by this operation, this O6 operation, and not by anybody else. So that's, I'll show B2 in a minute, but they're examples of bound builders. And then finally, when the for loop is done, we load the counter value into V7 and we return it. So that shows the sort of high-level structure of this loop, and then we can go and look at the body B2.
Is that a bound builder essentially just that, like, equivalent to this block of code as in it? Like,
the way I've been describing it is the way that I think of it, which is it's basically a builder object whose control in and out is determined by some other operation, right? And the perfect example of that is the body of a for loop, right? It's the for loop that determines how many times the builder object gets used. Same thing would be like the then side of a if, right? It's determined, its execution in is determined by the if block, and then the if block says once you're done, you go to the merge block, right? There's no, conditional branches happening, right? And as opposed to an if compare greater than instruction basically says, fall through if it's not, and if the condition is true, then you jump over there. But it doesn't say anything about what happens when you get back. Like at the end of that one, it doesn't say come back to this operation, and it doesn't stop anybody else from also branching to that builder. So it's unbound, right? It's not bound by this operation. So that's the basic idea. All rules have to be broken, but but that's the basic idea, right? All right, let's look at builder B2, which was a little bit shorter, so the font size is way larger for some reason. So this one, the for loop is what the for loop operation creates B2 automatically, so it knows that it's the body of the loop, so it actually gives it a name of loop body for you, but it would do that for every loop, so every loop could be called loop body, but you could change that name if you wanted to. Its parent is that B1 builder that we just looked at. It also has the same scope, function scope, and as this one says, it's bound to operation 06, right? So it also provides an easy way to go back and forth between, like, if I have 06, I can find B2 and go look at it. If I'm in B2, I can look at it and me and say, oh, I'm bound to 06 and find 06 in B1. That should really say B1 bang 06, but anyway, it doesn't right now. It's not a target, which means nothing else branches to it. And then its set of operations are here. So the control operations for the loop are not put into the body explicitly. It's the for loop op that handles the mechanics of iterating, and the body is just the code that needs to be executed for each iteration of the loop. So here we're loading the counter value, we're adding 1 and or the constant 1, adding them together and then storing it back in counter. So basically we're going to count as many iterations as supposedly the parameters told us to iterate, and then it should return the number of iterations that we should do.
Right, you said the incrementing is taken care of by the
iteration counting. So bumping I, checking to see if I is less than, like setting I to initial, bumping of I by whatever the bump is, and then checking to see if I is still less than the final to iterate again. Sure, that's all handled by the for loop.
Right. How does that work later on in an optimizer where, say, you want to tile? Like, would that complicate things in the fact that, B0 is doing the incrementing, this guy is doing the actual work?
I don't think so. That's a good question. Because in tiling, usually so yes, you have to understand in tiling, you have to understand how much data is being accessed by an iteration, and then how big the iteration space is that you need to keep the memory that it's accessing in cache. So yeah, it's going to be in 2 different places. But I mean, the alternative is it's like all kind of operations spread throughout anywhere, right? Like one of the advantages of this is that it provides a little bit more structure in the IL, so you know where look for things. Like you already know, in essence, I didn't have to recognize that it's a for loop. It's a for loop op, right?
Right.
Now, that doesn't mean you don't need the ability to be able to recognize a for loop when someone doesn't use for loop op, but it does mean that if you create code like this, you can very easily tell where the loops are and how many times they're going to iterate. What's the primary induction variable, right? It's all right there, called out in the code.
So I guess like because there is a parent target, you could find the parent
Right.
and then do the optimization
Yes.
tiling.
Yes, exactly. And you can even get, like if you're in a nested loop, right? If you're in the inner one and you're inside there, you know which builder you're in, you know what operation it's bound to, which gets you one thing out. And then from that one, you can get to its builder, which is bound to the next loop out, right? You can very easily find your way around. And in fact, the way one of the internal details of how the IL is arranged is that a pointer to an operation basically can get you anywhere. Like it locates you exactly in the IL somewhere, and then you can get anywhere else from there. Like you can go forward in the operation list, backward in the operation list, up to the builder that created it. Like you can go anywhere basically, or iterate the builders that are referenced in the operation and go down. Right? So you can go anywhere from like an operation star is a program location basically. So that's kind of a nice feature. Let's see. Okay, so yeah, so I think this is all I was going to say about the IL. I just wanted to kind of give people a flavor for it, and it's not perfect, as has been pointed out. There are lots of improvements that could be made here, but basically this gives you a flavor for what the IL kind of looks like, and then you know how you might move around through some of it and what kinds of features there are present in the IL. And that's the end of the second section of the agenda. So, allocators and memory. So, let's see. I did want to do a little bit of a preamble here on why this is so important for JB2, or why I think this is such an important topic for JB2, and basically it's because in JB2, it is the notion of potentially multiple compiler objects, which are can organize differently. So you could imagine a world where you've got a regex compiler, a Python compiler, and I don't know, something else compiler, all like the debugger uses a compiler too. So you could imagine all three of those things, all of those objects, all being involved in the same process, and yet their lifetimes may be completely different. You might not need the regex compiler all the time. You might want it sometimes. And you want to be able to get rid of the memory if you don't need it. And when it goes away, you want it to only take away its memory and nobody else's memory. And you want to be able to, if you have to, create these things and destroy them all the time and not sort of sabotage the memory safety of the program, of the process that you're in. So, so all of those things kind of mean we really need to be very careful about how we manage memory. I know this probably isn't very surprising to anybody who works on a JIT compiler, but it's a little bit of a different world from a static compiler where your management of memory, like you're the process, the process is for building a static compiler, so you're the memory. It's all your memory, whereas in a JIT compiler sense, or when you have multiple compilers in the same process, there's other people, other owners of memory that you'll have to collaborate with. And in principle, it gives you an option to be able to say, if one compiler in memory is really doing some high priority or high memory operation where it needs to suck up all the memory, in principle, it could ask other compiler objects to let go of some of its transient or memory that it doesn't need or could recreate, for example. So, make space for me because I need lots of memory, and then be able to recreate it. And again, you don't want anybody to sabotage, you don't want one compiler to sabotage another compiler ever. So, a lot of that is notional in that I haven't implemented all of that support yet, but it's part of the vision for how JB2 should work. And so I've spent some time going through all of the classes of JitBuilder and making sure that its allocation is sort of under control. It's not a fully complete process yet, but it's very close. Right now, it doesn't really provide any facilities to optimize the use of memory. It's a very simple allocator that's provided just use malloc and free under the covers. But the use and management of all that memory is all pervasive throughout the compiler at this point. There's nothing that's not using allocators that could use allocators. I'll talk about what I mean there in a minute. All right. So the basic currency of dynamically allocated objects is this base class called allocatable. It is a primary base class in JB2, and almost everything in JB2 is allocatable. There are some downsides to this approach, but it's kind of where it is right now. And it's, the fact that there is an allocatable object means it can be changed without necessarily modifying the entire code base again. So it basically provides two very simple things. It gives you the allocator that allocated the object and the size in bytes. So every object knows who allocated it and what the actual size of the object is. Now, sometimes you want to be able to stack allocate an object that can also be dynamically allocated. So that's also supported by having a null allocator and a null size. So basically, when you stack allocate something, you don't need to worry about its size or its who allocated it, because it's stack memory. It's managed by the compiler itself. But the allocator framework needs to be able to know that that's one of those objects is here, and it doesn't have to do anything special with it. So that's kind of a special case for that's handled, and that kind of pervades through some of the support when the objects in that you have to provide multiple constructors, which is kind of one of the most painful aspects of this, but it's not too bad in practice. Knock on wood, I said. All right, so obviously that's kind of this solution is not great for allocating arrays, because it means that every object in the array will also have this mem and size thing associated with it, which I'm not happy about this, but it is what it is for now. So there's overhead memory of that, and it's basically the first object knows how big the thing is, and everybody else sort of doesn't. So not awesome. I'm not super proud of this, but again, my main goal in starting this was just to get an interface in place so that it could be modified and improved later. And having these things represented in the source code as opposed to, invisible values that are stored behind the object pointer that you had to allocate extra space for, all of those things can be done, all those magic things can be done later and hidden behind this same API, and improve the ability to allocate, the efficiency of memory allocation. Like I mentioned, classes can support dynamic and or stack allocation, and there's a bunch of helper macros that I've defined that are very similar to like tralloc that used to exist, or it still does exist, I guess, in Testarossa. There's a JB alloc, there's an allocation category, all very familiar to Testarossa folks, which you just insert JB alloc and name a category. You can put that into the class definition in the header, and that will take care of making sure that you can allocate this object and that it has a category that will be associated with it when it's allocated. And then in the class file, you do this init JB alloc cat, and that just takes the class name and the category, and it will register that category when that class is in the compiler when that class is used. There are also some helper macros that I've defined for simplifying the definition of constructors. It's not very much simplified, so I don't always use them. But the basic idea was I created a thing, a dynamic alloc only. One of the reasons why, didn't I talk about the, interesting. Okay, all right. One of the things that another pain point that came about from implementing it this way. So it like Testarossa allocations, it uses placement new to provide the allocator into the allocation process. But I found in order to support both stack and dynamic allocation, I needed to not only use the placement new option, but also have the allocator provided as the first parameter. So when it's stack allocated, you don't provide an allocator, and when it's dynamically allocated, you do provide the allocator. So there's a double sort of parameter that you need to provide in dynamic allocation cases, which means you need to have two constructors, one for dynamic allocation and one for stack allocation. So dynamic alloc only defines that dynamic one and automatically appends an allocator, or not appends, prepends an allocator parameter to the constructor arguments for the class. And all alloc allowed basically just doubles up. It does it defines two constructors, one with the allocator parameter and one without, so that you can do both. And then yes, you got to go and implement both of them. And yes, that's a pain. And yes, I don't like it. But at least it's a thing you do once when you create the class and you create the constructors. And then when you're actually going and allocating objects, it's actually pretty straightforward to use and easy to use. So it's pain on the developer side, but on the use side, it actually looks pretty reasonable. Let's see. Fun fact, yeah. So I created this bat alloc. I happened to notice that bat alloc, if you did it backwards, you could actually make a name that's in hex that sort of looks like bat alloc, right? BADA. One is like LLL0C, right? OC, right? And that has a nice property that it's actually not aligned, that value too, right? So anyway, nothing actually uses JB2, but if you ever needed to write, like overwrite a pointer or leave a pointer around for like paint memory or whatever, it's not an unreasonable thing to paint memory with to, and it has that kind of battle. I like the battle look. The
Patented.
Battle look backwards. So anyway.
Look at my core dump with a mirror.
Yeah, exactly. All right, so I thought I'd put an example of this so you could kind of see what it looks like. This isn't the whole code for string. I have my own string class because I didn't really want everybody using standard string directly, although my string class actually has a standard string in it right now at its core, but it's hidden within string, so nobody actually directly accesses it. So again, the API is clean and means it could be replaced later. So I just want to write a string class, like a real string class. So this JBalloc thing, basically says I need to be able to do allocations of this thing, and it will create a class, a category that's associated with string for string. And then the constructors are, in this case, I thought it was, people are likely to want to create strings on the stack as well as dynamically allocate them, right? They don't want to always have to dynamically allocate a string. So I provided all alloc allowed. There's a no args version just for macro craziness. It's preprocessor crap. But the var arg stuff works better if it knows there's no, if there is vargs. There have to be args to use the var arg stuff. Anyway, so in this case, you can create a string, an empty string basically with no arguments. You can pass a const char star to it. You can pass another string to it. So those are the three constructors that are supported. And then in the CPP file, remember that's that init JBalloc thing, which provides some more implementation behind backing for the allocation process, for the ability to allocate, and then implementations for 3 times 2 constructors, and yes, they're duplicated, and yes, they're a pain. There's a few classes like compilation where this gets really bad because compilation has lots of fields and it has like 4 constructors that have all the same fields being defined. So yes, that's awful and ugly. I don't like it. In fact, I think in compilation I even used a macro for the field, so I didn't have to have 4 different versions of 20 fields being defined similarly. But anyway, yeah, so that's kind of just how this works, right? So you can see that the ones for dynamic allocation have an allocator A, the ones that are for stack allocation do not have an allocator, and they just call into allocatable with either with an empty thing or with an A, and that's how it determines later on. So if somebody calls, because JBalloc is overriding placement new, creating deletes, doing all that stuff under the covers. So if someone happens to do a delete on a string that's been stack allocatable, delete can tell that it was stack allocated and it doesn't have to do anything with the memory. Whereas if it's called on something that has a valid allocator, it will ask the allocator to deallocate the memory. So on the user side, if you want to create dynamic strings, so you can use the 3 things, and here's where you see the double thing, which is it's a little bit ugly, but it's not too bad. You get used to it pretty quickly, and otherwise it just looks like a constructor, and then you can delete them later on as you like, because obviously these are allocated, so you need to deallocate them. So there's no bulk free right now, and then in stack allocations you don't need to do an allocator, so these ones look pretty much like you'd expect them to look for a stack allocated object. These ones are quite easy to use because there's no allocator to be provided and they're automatically deleted themselves.
So is it your design goal to have the users of this manually manage the lifetimes like this?
Yeah, so I'll get to some of that soon. This is kind of a state of the way things are right now. So yes, right now, all of the objects are being manually deleted, which hasn't been as painful as I had thought it might be, but I do still think that a bulk-free allocator is a better choice for doing a lot of this stuff. But right now, I don't have a bulk-free allocator, so I've got a few deletes sprinkled around, and it has been a pain. But I'll talk more about that in a sec. So,
sorry, can I ask about the stack allocated strings there for a second?
Yeah, fire away.
Right. So conceptually, the string object itself is allocated on the stack, but doesn't it represent probably some kind of heap allocation in behind it that actually contains the text?
Right, but that would be a separate object being allocated and managed independently of the string itself. So the delete's still being called, and if there is an underlying thing like that, then it needs to be handled, right? So a better example, so string in this case is backed by a standard string, and it's actually an embedded standard string, so there's no actual dynamic allocation happening. But you can imagine for something like list, where it has to manage items, and those items are dynamically allocated. So when you create a list, you actually have to provide even if it's a stack allocated list object, you have to provide an allocator for the items to be allocated.
Right.
So
I guess the standard string is often going to do a heap allocation, but not related to your allocator, right? I guess it's just going to do the default global new delete thing. But this API for stack allocating the string forces you to continue doing that. If you want to change the implementation, you can't specify an allocator here.
Yeah, you're right. That's probably true. Yeah, you might have to think about that later on. Strings are actually string objects are immutable at the moment. You can append to them, but actually, now that I think about it, that's not true. You're right. You're right.
Okay, well, it was just a thought that.
Yeah, that's a good point. You're right. So it's not a perfect isolation. Let's put it that way. But at least some of the notions are there. But you're right. There will probably need to be more allocator things strung up inside. Okay. Oh, I missed an allocator that's supposed to be bolded and fonted in red. Anyway, right. Okay. So let's switch over to the allocators that are there in JP2. So the allocator API right now, so there's a class called allocator, which is the base class for all of these things. Allocator is actually allocatable, I think, or maybe it's not. Maybe it's one of the few that isn't. Can't remember now. In any case, no, I'm pretty sure they are allocatable. Anyway, there's not much to the API right now. It's basically an allocate, deallocate, and there is a little bit of sort of other, you can specify a minimum allocation size. So if you wanted to do like a segment allocator, it provides a little bit of support for doing that, but nothing actually does this right now. Everything's using a minimum allocate size of 1, so it's just allocating through malloc and free, or allocating through malloc and freeing through deallocating through free. And it does have a little bit of support for allocation categories like in Testarossa, but I don't know that anybody feels like that's super valuable, so I might actually remove that at some point, but it's there for now. And you can ask an allocator if it's the same as another allocator, but nothing's actually. Oh, sorry. You can ask if an allocator was used to allocate a particular object by checking that object allocator thing. But anyway, it's just a convenience thing. There are 3 actual concrete allocators that are defined right now. All 3 of them are extremely simple. Allocator raw is just uses malloc and free to do allocate and deallocate. There is a tracer allocator, which is a concreate allocator that basically just output method. You give it a text logger object which corresponds to an output stream, and it just spits out messages whenever you allocate, deallocate, so you can trace what's going on with some other allocator. And then there is also a tracker allocator, which isn't super useful, but it just kind of verifies that you have, you know, in this case, because there's no bulk free, it tracks that the number of allocations and deallocations matches at the end of the process. So at the end of the when the allocator is destructed, it checks to see that you've deallocated every byte. You think you've deallocated every byte that it thinks it allocated, and that the number of so that the number of allocations is the same. Sorry, I'm saying this poorly. That you deallocated every memory region that you think you allocated, and that the total number of bytes that you allocated is the same as the total number of bytes that you think you've deallocated. So it's a little bit of a validation on doing that you've done things properly, but it's not super rigorous. I 100% agree with that. I'll talk more about that in a minute too. How you configure and use them. So there are a few life cycles that I've sort of defined already as part of JB2. So there's every compiler has an allocator. So you can ask a compiler for its memory. So if you need something that's tied to the same life cycle as the compiler object, i.e. crosses all the compilations, crosses all the runtime of the code that's been compiled, then you can ask the compiler for its memory and allocate things there. The compilation itself has an allocator which you can ask and use. The IR has its own memory allocator, so it can be the same as any of these things, but you can ask the IR specifically for the memory that was used to allocate this IR, all of the objects inside the IR. And pass, so optimization passes, you can get a memory that's specific to the pass. So it's allocated at the beginning of the pass, and when the pass ends, it will be, that allocator will go away.
I have a point that I just thought about looking at this in terms of allocated placement new and fast.
Yep.
You could enforce an API where instead of the user having to do new mem string, you could have a static method that allocs, and then you just pass the mem and everything, and inside of it, it does it, so you don't have to have placement news everywhere. You can just use that just to clean up the code. If you're forced to have to pass the allocator both to the placement new and the constructor, you could just hide that away, so you as a user only have to pass it once.
So when you do a new, oh, I see. So the new,
like it'll be like a factory method, right? Like where the factory would do a new whatever, send it back.
Right.
And it would
so then in user code, you wouldn't use
the new, yeah. It would just be cleaner and less error prone than having to do new and deletes manually, right?
Maybe. I can look into that. I mean, it's a fair amount of code to change now too, but it's still not. It's easier to change now than later. All right. Yeah, let's talk about that more later a bit. Right. So I already kind of talked about this. So basically, you can allocate. It's again, that's the same double thing here again. The tracer and track allocators can be automatically configured based on the config that you send into the compiler. So there's a set trace or track compiler allocations that when the compiler creates its allocator, it will actually automatically allocate a tracer or a tracker allocator to with the parent as the actual raw allocator. And similarly with the compilation, so it'll check this flag basically to see whether or not you want that turned on.
Are they mutually exclusive?
No. Okay. It's just a string of, like, every allocator has a parent allocator. So if it doesn't know how to allocate something, it asks its parent to allocate it if it has it. So the tracer and tracker allocators, all they do is the tracing and the tracking, and to actually allocate, they call the parent, which is usually a raw allocator. So it's just a very simple delegation framework. Status and future directions. So I run everything with Valgrind, looking for leaks, and I went through a process of a few days, cleaning the hell out of everything. And once I got clean, I added Valgrind into the C tests that I create for all of this, so it runs everything right now. Every test that runs with Valgrind. writing of memory or reuse or double freeze or anything like that that Valgrind can find, the test fails. So I can guarantee that there are no leaks right now in the allocator objects that I manage. I guess under the covers too, since Valgrind knows nothing about my allocator framework. There are currently no tests to test cross-contamination, but not everything allocates through a memory allocator that it can get to, and there's no way, other than a parent field in a compiler, which nobody ever sets, there is no way to get from one compiler object to another to get another compiler's allocator. So I don't believe that there's any cross-contamination right now. There are still a couple of uses of STL. There are a bunch of standard maps and a bunch of obviously standard string that's inside string that doesn't use this framework. So there is still memory allocation that's happening that does not have anything to do with my allocator framework. I'm hoping eventually to get rid of those, but I've been too occupied with other things to go and write my own hash map. So, and it's the OR string class.
What data structures did you create?
There is a list, there is an array, there is a bit vector, and there is string. I think that's it, plus all the iterators that allow you to iterate over, well, can't iterate over a string, but iterating over the other containers.
Okay.
So it's a very basic set right now.
Does list look like the original Testarossa list? Or is it your own?
It is a doubly linked list, and that's basically, I guess it's another implementation of a doubly linked list. So it doesn't look exactly like the original Testarossa list, but more or less similar power. Just to say not much. It does maintain a set of list elements, and the list elements are linked in a doubly linked list. That's it. So you can create forward iterators, backward iterators. It does check, the iterators do check to see whether or not the underlying container has been changed since the iterator was created. And you can, I checked this actually after Erwin asked about it in the last one. You can create an iterator that cares about the underlying container changing or not. So you can be bothered by modifications or not be bothered by modifications. And it creates a copy of the elements when it does it. So you'll always get the iteration of the thing that you asked for an iterator of. And then it will continue to, when you ask for things from the iterator, it will continue to check whether or not the underlying container has been modified before it returns an item, if you've asked it to do that. Otherwise, it won't care. It will just give you the iterated version that you asked for. Future, I think it would be a good idea to recreate some of the allocator styles that are there in Testarossa, although I haven't thought very deeply about it at this point. And I would like to support some additional life cycles other than the ones that I've got there right now. Again, kind of oriented towards the things that people do with compilers and the types of data that people manage in compilers. And then sort of more along the lines of integrating with other things would be, I would like to create an OMR port extension, which provides an allocator that's backed by the OMR port library, so that JB2 can use the port library, and then you can do the same thing with OpenJ9, so that you could be backed by OpenJ9 memory segments if you wanted to, which would help with integrating JB2 stuff into OMR or into OpenJ9. All right, 52 minutes, and we got through 3 of them. So, and this was probably the most complicated one, so save the best for last when my throat's already starting to go. But anyway, so I did, sorry, I guess I should pause. Are there any other questions about allocators before our memory management and JB2 before we move on? Yeah, I've had enough of it too. All right, extensibility. So I gave a brief summary of this at near the end of the talk last time, which basically covered me. I think I have this. I think I presented this in the, yeah, I did. So basically, there are static extensibility mechanisms supported in JB2 and used all over the place, like inheritance and component proposing. There are also dynamic extensibility, so most of what I'm going to focus on in this section are the dynamic extensibility ones, but I'll very quickly go through the fact that there is standard C++ mechanisms that you can use. You're allowed to extend things, like subclass things. In fact, there's lots of examples of this throughout the code base, and in fact, I think this is the primary mechanism for doing extension because it's just the one that C++ does well, as long as it fits the use case that you're trying to fit. So, you know, the best example of this is compile unit is a base class that's defined in JB2, which is kind of not a very useful thing because it doesn't know about what entry points it's got, what it's doing, how to pass values in. So there's in the func extension, which has its own namespace called func. I should say it's a function extension, but it's in the func namespace, defines a compile unit called function, which is a subclass of compile unit. And the expectation is there that, you know, you'll create function objects rather than compile unit objects. Compile unit objects aren't very useful in and of themselves, but a function object is because it knows about that it has an entry point. It knows that there are parameters. It knows that there are local variables in the stack frame, etc. And then there's an extension called VM, which has all of the virtual machine stuff from the original JitBuilder API. Actually, I shouldn't say all of it. It has most of it. And it defines another subclass, a subclass of function called VM function, where it basically sets you up to have a bytecode builder as the entry point rather than a builder as the entry point, so that you can pass VM state around very easily. And then the expectation is that you'll be creating VM function objects and not just function objects. So inheritance and subclassing is a very well accepted thing and used all over the place. It doesn't mean you can't use the subclass, but you know, obviously the subclass functionality won't be in the superclass if you use it. That's the main thing. Virtual functions encouraged. Composition can be used. The best example I could come up with is list, which there are lots of list objects embedded in other things. That's a composition. And as I mentioned, the items need an allocator to be able to allocate them. And probably string will have to get one at some point too. Thanks, Devin. Static polymorphism, which we've been using in the OMR compiler, isn't specifically prevented, but I'm not using it anywhere, and it's not really a favorite approach. And the main reason for this is because I'm intending JB2 to be more of a dynamic extensible thing rather than like you're loading extensions at runtime. You're not creating a compiler and sort of arranging all the pieces statically and then compiling them and building them all together and then running that thing. It's more of you assemble things at runtime together.
Sorry, just one quick. So func and VM? What are those?
They're namespaces, but they're namespaces associated with a particular extension. So in JitBuilder 2, I put every extension that I create, I put in its own namespace. And I have been using OMR JitBuilder as kind of the root, but I found out that you get very long symbol names if you have very deep namespace hierarchies, and that actually makes your executables larger by a measurable amount. So, because every symbol's got an OMR underscore JitBuilder underscore blah underneath it, so you replicate that times every symbol in every library, it actually turns out to be quite a lot of space that you're wasting by doing that. So I'm probably shortcut this down. I might actually just put this into a JB2, everything into a JB2 namespace, and then extensions I might not even have in the JB2 namespace to save that again. But anyway, that's kind of future. I'm not that concerned about it, but I did notice that my library sizes were much larger than I expected them to be, so I started looking at it at one point and it's like, holy crap, it's like so much string. Like, yes, it gets smaller if you strip out all the debug info, but the symbol names are just like, they're enormous. Anyway. All right, so dynamic extensibility. So JB2 implements a dynamic extension mechanism that's basically like being able to add a mix in. So it allows you to attach what I call add-ons. So you can have an object that has an add-on that's attached to it, and then you can sort of structure these things. And there's some mechanisms that JB2 provides to make this work easily. So as an example here, the base extension attaches an object called a base IR add-on. So that's going to be add-on to the IR object. So in an extension, you can create new operations, new types, new symbols. Basically, you can create things that the base infrastructure has no idea about. but you need to be able to represent those things in the IR object, and you need to be able to, make sure in the case of, say, the base extension, you can create pointer types and struct types, but you don't want to create like the same pointer type over and over and over again just because you need a pointer to an int32. So you need a place to be able to sort of capture that, here are the pointer types that are here. And yes, it could be the type dictionary, but you got to look things up all the time. So in this base IR add-on, there's a standard map which actually records which pointer types and struct types have been created as part of this compilation, and then you can and then it uses that to do it. But pointer and struct types only exist in the base extension, so that standard map can't really exist in the IR, and I don't want to limit the kinds of things that you can do. So it creates this base IR add-on, which is just an object that holds those standard maps and allows you to access them very easily. And then it uses this infrastructure to attach them to the IR object. So the example here, you get your hands on an IR object, which there's one hanging off the compilation, so that's easy. And then you can allocate one of these base IR add-on objects, and one of the things you pass to it is the root IR object, so it can kind of get back and forth. And you have to use the same allocator as the root object in order to allocate this add-on, so that its lifetime matches the lifetime of the object, or at least matches the lifetime of the object that you're attaching it to. And then you just, on the root object, you say attach one of these things with this type and pass it the object. And from that point forward, you can then get it from anywhere. So what's this point saying? Oh, yeah, okay. So the code that I just showed is just basically showing you how you create and attach it, but how do you know when to create and attach it? That mechanism is managed by the compiler. So it basically gets notified when an IR object gets allocated, so that so that the base extension knows that to attach one of these things. Basically, there's a registration and notification process that allows that to work. And I'll go into more detail on this. I know I'm covering it at a very high superficial level here. And then finally, to use it, anybody who can get their hands on an IR object by getting it from the compilation again can just ask for the add-on for the base IR add-on. So any code that knows that there's a base extension around can ask for that add-on and access it. But other code that doesn't need to know about the base extension and may not even and there may not even be a base extension around, doesn't need to know about this class or this process or any of it, right? So it's the base infrastructure doesn't need to know about this in order for another extension to be able to do it. Okay, so how does that actually work in a little more detail? So there's a few mechanisms here. So add-on and extension are kind of two of the ones that I've mentioned in passing. There are actually 5 classes here that are kind of working together to make all of this work. There's a base class called extensible, and a lot of the objects in the DB2 code base are actually derived from extensible, either directly or through something else. This provides some functionality for the compiler framework to be able to allow things to attach add-ons to various objects. At the core of that is a thing called kind service, which helps to assign categories of things so you can talk about the different types of things. And I know that sounds a little bit like RTTI, and I'll talk about that in a minute, but don't get too excited about it yet. Extension is sort of the base class for creating these plugins, and I recognize I didn't actually talk very much about extensions in this talk, so it's one of the things I can talk about in a future talk. But I mentioned, like the function extension or the base extension or the VM extension, or there's a debug extension. Those things are ways that you can plug functionality into the compiler, into a compiler basically. And it also participates in this and helps manage some of the notification registration bits for this. Add-on is another base class, which add-on actually extends extensible, I believe. It's basically, if you want to create some of this function that can be tacked into, say, attached to another object, you have to make it a subclass of add-on. And then compiler also participates in the registry and notification for extensible objects. And I'll talk about some of these mechanisms in a little because it's kind of at the base of everything. And then I'll talk about add-on a little bit more and kind of reference the other things. So I'm not going to go through 5 sections of stuff here. I'm going to kind of do it in 2 bits, but once you've seen add-ons, I can talk about how the other bits kind of play a part in how this all works. All right, kind service. So as I mentioned, it's kind of analogous to RTTI, but there are reasons why I didn't use RTTI. So I created a thing called kind service, which basically allows you to create categories of classes within the compiler independently. They don't have to match your actual class. You don't have to define a different kind for every class, but it's common to do that. And there's one that's in particular that's important, which is the one that's inextensible, but I'll talk about that in a minute. So the way a kind service works is that when you create a subclass of the kind, it basically registers with the kind service to assign an index, a kind. Well, it's not actually an index; it's a bit vector right now, but it assigns a kind which captures, objects of this class will all be marked with this kind. And then from the kind, you can tell which objects are related to other objects in the hierarchy. So, when it allocates a base class, it gets a bit vector that's the kind for that base class, and all objects that are allocated of that base class will get that kind. When you create a subclass, it registers and says, all right, give this guy the next bit, and he gets that bit. And so basically you can do an and between the two and tell that they're the same. If you and 2 objects kinds together and you get one of them's bits back, then you know that it's a subclass relationship, essentially. And so every object gets kind of annotated with this subclass that it's allocated with. So you can it's not the same thing as being tagged with a VFT, and obviously things have VFTs in the C++ classes, but it's a visible implementation of a class hierarchy relationship. And then if you have kind service inside an object type, it provides some useful convenience functions for asking about what an object is. So you can ask if an object is an exact kind. So if T is a particular kind, you can ask if object is exactly a T. Or you can ask if T is a subclass, or sorry, if the object is a subclass of T, or T. And you can do downcasting very simply without having static casts sprinkled throughout the thing, and it does an automatic assert to make sure that it actually is one of those things. So this is probably all sounding very much like what RTTI would provide you, but basically the most important kind service is inextensible. It's the one I'm going to focus on here, although there are a few things in the compiler still that have different kind services, and I'm getting rid of them and making it all into extensible. Why not just use RTTI, you're probably thinking. So kind is currently a bit vector, so that it's very easy to kind of mask things together. So you can do the is exact kind and is kind, or is kind is the easiest one. But I'm eventually going to change that to an ID. So it will be, so then basically kinds turn into a contiguous set of IDs, which you can use to do higher performance decoding and dispatching for various extensibility features. That wouldn't be possible, I don't think, or clean with with RTTI if that was the mechanism, because you don't have as much ability to use what RTTI is doing. It doesn't let you build, I don't think, VFTs and other kinds of things. So basically, I think I can do some useful optimizations to make this dynamic extensibility framework more efficient by not using RTTI and having control over how these things get assigned. But I guess that remains to be seen because I haven't actually done it. All right, so what does kind service support actually look like? So if you have a class that you want to assign a kind to, like for example, function compilation, which is a subclass of compilation. Compilation is a JB2 core class. Compilation itself extends extensible, so it's in the hierarchy here. So in the class definition, you do a subclass kind service decal, I don't like this ordering, but it is what it is right now. And basically it knows extensible, because you can have kind services for multiple categories, not just extensible, you can create other ones. It passes this extensible thing to say which kind service are you talking to, and then function compilation is the class that's getting the support for a kind. And then in the CPP file, you tack in subclass kind service simple, provide all the names of the things that you're working with, right? So function compilation, its name, I'm going to get rid of that. What the superclass, what the base class, the immediate base class is, and what the category of kinds is. And then basically you add a public constructor which passes in the kind for the current object. So function compilation, you can get its kind by saying kind extensible, and that basically works out to a static call to a function that is defined by this guy and implemented by this guy automatically under the covers. And it basically just it asks the kind service to give it a bit, basically, and it says, it takes the base class, asks for the base class for its kind, assigns a new bit, ORs them together, and says that's your kind, right? Because you're one of those things, but I need a bit specifically for you, so that's how it works. And then it does it via a static call to make sure that I originally tried to do this with static blocks, but because you can't guarantee the order of static block execution, I changed it into a static call, which you can actually make it do things properly. It will actually get the right answer in the end. Right, and then if you want this object to be further extensible with other subclasses, then you provide a protected constructor that actually accepts the kind, so it just gets passed straight in. So it's not my kind, it's whatever that subclass's kind is. And that's pretty much it. So it's not too bad. This part I don't think is too painful, and it's hidden behind some convenient stuff that's fairly easy to use. Now, add-ons, so this is the second sort of major topic here. So add-ons are just the things that can be attached to other extensible objects. It's basically a way to optionally augment an API. So if an extension isn't loaded, then its add-ons won't be created or attached to anything, so it won't impact anything, nothing can access it. But once the extension is loaded, it can tack in its API into the objects. And it means that you don't have to, it means that objects can be allocated anywhere throughout the compiler without knowing which extension APIs have to be added to it. And that's the notification mechanism that I'll talk about shortly. These extension objects are the things, so the extension object represents a plugin, so that it basically typically creates an add-on. It's the thing that's creating add-on objects. And so I'll expand on a couple of use cases that I've had so far. So you can attach a new API to a specific object. So in the case of the JB extension, so JB extension is a thing that provides native code generation via calls to the OMR JitBuilder API. So that's the previous version of this library. The JB extension itself listens for new extensions to get loaded by a compiler. So it can register with the compiler to say, hey, tell me when new extensions get loaded. So if somebody loads a new extension, I want to find out about it. And using that mechanism, it watches to see if, for example, the base extension gets loaded. And if the base extension gets loaded, the base extension adds a whole bunch of operations and types and things. And so it needs to be able to generate code for the base extension to be able to generate code for it. So it creates a base extension specific JitBuilder code generator. So and then attaches it to the base extension. I'll go into a little bit more detail on this too. I just wanted to kind of give the basic flavor of the idea, right? So there's a code generation object that's taking care of how to generate code. If the base extension gets loaded, you need to tack in all the stuff that it needs to know how to generate code for that extension's IL. And if another extension gets loaded, you need to tack in the API that knows how to do that too. But if those extensions aren't loaded, then there's no way to refer to the IL of that extension if that extension hasn't been loaded. So you have to kind of do it optionally, right? I can only talk about, what's a good example? I can only talk about an add operation if the base extension is loaded. So I can't add API to the code generator unless base extension gets loaded in order to talk about it. I'm not saying that very well.
When you actually use one of these APIs, you have to know that you're using it for the base. Like it would be some kind of template parameter, and then you say add or something like that. It came from base extension, therefore did this.
So the base,
or it would be like template for the add-on, and then
so you mean like how to create an operation?
Well, more like how would you like use an operation from a base extension?
Right. Okay. So this is why I should have actually done a talk about the extension objects first. So the extension object is like I said it earlier, but I probably should expand on it a little bit. So the extension object, like the extension object represents a plugin. So I talk about the base extension, but there is actually a class called base extension, which is in the base extension. Right? And the way that you create objects is by calling. You use a pointer to the base extension. You say base extension arrow add, and provide the operands that it needs to do the add. Right. So that I did talk about that a little bit in the previous talk, but I just showed a few examples and kind of zipped through it. It's just like if I were to pull up the base extension class, you would see a whole bunch of public stuff in it that's like, here's int 8, int 16, int 32, float 32, float 60, but here are the types. It doesn't have any symbols, but it defines, there's a way to create pointer types, there's a way to create struct types, and then there's all these operations that you can use, like add, sub, mul, if, compare, greater than, if, then, else, for loop, else. And so you call all of those things off of the extension object, and it takes care of creating it, adding it in.
And so I'm assuming it has a pointer such that the code generator knows how to deal with it, because if the code generator is very generic, it probably needs a handle, right?
Yes.
Okay.
Yes. So the way it works is, in this particular case, the code generator basically picks up an operation. So it only knows about operations. Right. It picks up an operation. It says, which extension created you?
Okay.
And then it delegates to that extension object. I think I show this later on, but it delegates to that extension to say, use your JB code generator add-on to generate code, and it provides some other pointers to stuff that it needs to do that. So it's a delegation mechanism. It's hard to explain, but it's like I'll show code later.
So is the set of APIs also an add-on, or is that the extension, or the code generator has an add-on? The code generation's extension is called the add-on, but the public APIs is just called the extension. Is that how it works?
I'm not sure I followed your question. Try asking one more time.
Like, you have add-on, like the class add-on.
Yeah.
Is that when you said, I want to create an add prompt?
Yeah.
That's is the thing that's calling, hey, give me an add operation object. Is that an add-on itself, or
no? So the thing that creates operations is the extension object.
Okay.
The extension object is a subclass at extensible, but it's not an add-on.
Okay.
So you can't add an extension to something, like an extension object to something else, but you can add add-ons to an extension object.
Oh, okay.
Probably need some diagrams to go through this in more detail. I recognize that there's a lot of text here. Sorry, most of these slides were created in the last 2 days, so not much time to create diagrams. 10 minutes. Awesome. So I did make it to the end. Okay, or will make it to the end. Okay, let's skip the second example. So there's an example where, different objects get created and they need to have stuff tacked into them. And the example of that is the IR one that I used before, right? So IR objects get created by compilation objects, by compilations, and you need to be able to tack in add-ons into those objects. So there has to be a registration notification thing for when those objects are getting created, so that you don't have to know all the places where a thing got allocated in order to augment it to add on the thing. Like, you don't want to have to do that. So there's, anyway. So I'm going to focus on this one I've talked about the least and quickly, just because I think it's gave is not actually really implemented with add-ons right now. So conceptually, it will be, though. All right, so here's what the base IR add-on looks like, this code. So it's a little bit simplified, but as I remember, I mentioned that the core IR has no idea what a pointer type is or a struct type is. That's only in the base extension that you can get access to those things. So this base IR add-on is a way of tracking which pointer types have been created so you don't create many of the same kind. Don't worry about base add-on right now. So it's allocatable. It has this base extension object as a friend class because the constructor is protected. I don't want just anybody creating these things. And then the public API for this is basically give me the pointer type from a base type and register a pointer type. So if I create a new pointer type, I want to be able to register it with this mechanism so that nobody else creates it. And then if I have a base type, give me the pointer type for it, and that might end up creating a new type, a new pointer type as well. So when I create this thing, obviously I remember it has to be dynamically allocated, so it has an allocator passed in. It needs to know about the base extension object, and it needs to know which root object it's being attached to. And then add-on basically just takes all that stuff away, right? So forget base add-on in here. It's just essentially add-on because this stuff really just gets passed back into add-on. The only reason I have a base add-on class is so that this can be an actual base extension and not an extension. So it's easier for people to get access to the base extension object. All right, and then it adds this standard map, which maps a type, any type, to the pointer type that points to it, to that, like to point to objects of that type. So if somebody calls pointer type from base type with int32, it will hand back a pointer to int32 thing. If somebody else asks for it, it will hand back exact same type. It will create two different pointers to int32. So you'll never see, you know, T5 is, or not T5, T13 is pointer to int32, and then T15 is pointer to int32, and then T20 is pointer to int32. Everything will be T13 pointer to int32 if it's using that. Only one example of it. And then it needs to be part of the extensible add-on kind service, so it gets its own kind, and then later on you have to do the impl for it as well. And then how do these things get created, right? So base extension, when base extension is being constructed, so when you load an extension, it calls the constructor, it builds a base extension object, it creates that object, and as part of constructing that object, it says, hey, register me for seeing allocations of the IR extensible kind, like the IR objects. Basically, any object that has kind IR, notify me about that, right? And there's a bit of ballet that happens here. It goes down to extension and then over to compiler. Compiler is the thing that's actually doing the registration notification. So when you do this register for extensible thing, what it actually does is call into the compiler's register for extensible, and that thing just remembers a list of extensions that are interested in allocations of this kind, right? So this is a standard map which takes a kind and maps it to a list of extensions. So it finds the list that corresponds to this kind, and then it adds this extension onto the end of that list. Now, obviously, you might have to create a new list if nobody's registered for it before, but that's the basic idea. And then, so now if an IR object gets, so you've registered to be notified, so what happens when it actually notifies? So in the constructor of IR, it does a notify creation thing and says what its extensible kind is. So this as the last step of the constructor. So we've completely created this object basically, and we're just about to return from its constructor. So we notify the compiler that this object type has been created, and then the compiler calls this thing called create any add-ons for this extensible object. This is the one that just got created that has this kind, and then it goes and checks that same thing, and it looks up in the kind to find a list of extensions who are interested in this kind, and then it walks down that list. And for each extension that it gets there, it calls create add-on on the extension. So the extension knows how to create the add-ons that are necessary for this object and passes in this case, it would be the IR object, but it works for any extensible object. And then finally, the base extension implements this create add-on callback, I guess. And as part of that, it says if the kind is IR, and it might have to register for different ones, so it might have to decode what kind of thing it actually is. In fact, I could probably extend that by adding the kind, but I wouldn't have to look in the object. But basically, then it takes the allocator that was used to allocate E, allocates the appropriate add-on that's needed, and then calls E attach, and it just attaches that object onto there. So now, that IR object, as it's passed around through the compiler, nobody has to know that that add-on is there unless they actually want to access that add-on. And so, some function somewhere that knows that the base extension is loaded can then get that IR object from the compilation or wherever, and it just uses this template form to get access to that thing very easily, and then it can, ask for the pointer type for some base type. So on the consumption side, it's pretty clean looking. 5 minutes. Status and future direction. I think I made it. So right now, most but not quite all extensible classes are subclasses of extensible. Some of them I've gone through, as you might imagine, a process of discovering how to do this. And so not all of the code base is currently in the right state, but there is some vestigial stuff of like context, for example. I think I fixed context recently, but context used to be have its own kind service that was independent of extensible, and so it couldn't participate in all of this stuff. But it's really just needs to be folded into the extensible kind service and have an extensible base class and as its base class, and then it can participate in all of this stuff. I have currently 3 add-on implementations that are working quite cleanly and look nice. So one of them is the one that I just showed, the base IR add-on. There is also an object called IR cloner, which is basically a helper for taking an IR object and making a complete independent clone of all the objects inside the IR, using in possibly even a different allocator. So it basically just makes a copy of the IR that can then be, you can do anything you want with it. So that was motivated by the debugger, because the idea there was if you're in the middle of a compilation, you take a snapshot of the IR and the debug object knows what that IR was, and then you can even let that compilation proceed and have the IR finish and it can generate code, but you still have a copy of the IR as it existed at that moment, which is tied to the debugger. The debugger can walk through that and you can debug it, and you don't have to hold on to the compilation throughout that whole process. Anyway, and then base function extension add-on is also, I'm probably going to get rid of this one actually, but it basically adds some additional API onto the function extension object. So if you load the base and the function extension, it adds on some API into the function extension, but it's not really, I don't think I need it. The way it was implemented before is, so basically the functions that get added are, they're helpers for creating increment operations. So there's, in the base extension, it used to have an increment, which you give it a symbol, actually you gave it a local symbol and a value. And it would basically just do the load of the local symbol, add the value onto it, and store it back into the local. Now, local symbol is something that only exists in the function extension. Function extension is what gives you local symbol. So the API is kind of, it requires both extensions. And I don't want to make the base extension dependent on function, because I imagine that there are other compile units that aren't functions that you might want to use base extension functionality with, like traces or basic blocks or other things that are not functions. So I don't want to force the loading of the function extension in order to use base extension. But so I can't talk about a local symbol unless the function extension is loaded. I can't talk about add unless the base extension is loaded. If they're both loaded, then I can do that. So the idea was you add this increment helper onto the function extension so that you can add increment on top of the, if you do have both of those, you can say, I want to increment this symbol with this add. Local symbol. I fixed that very easily by saying it doesn't have to be a local symbol, it can just be a symbol. And then everybody knows about symbol. There's no more dependency on the function extension specific concepts, and so I don't need it anymore, but it's still there right now. There are also a couple of facilities that currently exist in JB2 that I haven't yet migrated to using add-ons. One of them is called Extended Pass, which is how the JB code generator crap is actually, is actually implemented right now. But an extended pass is really it's a more limited notion of add-on that I didn't realize could be generalized when I built it. So basically, I created extended pass, and then I was like, this doesn't have to be so limited as just to be done for passes. I could do this for anything. And that's when I created add-ons and moved it up. There's also validity checking, which is another painful topic for operations. You know, the idea is that it shouldn't be possible to create an incorrect operation. So, for example, you shouldn't be able to create an add operation, well, at least under the current way that this works. You shouldn't be able to create an add operation that adds an int32 and a float32 because the types are mismatched. So your add operation should have matching types. So it should add two int32s and create an int32 or whatever you want to define it, however you want to define it. And there's a set of validity checker things that go through and make sure that that's all the case. And there's base test things that test that you can't create incorrect ones. But that mechanism could really make use of add-ons, and instead it uses a very, you know, because like checking the validity of add, for example, in the base extension, you could check that add is consistent with int32, and it generates an int32. What happens if you create a complex extension which adds a complex float32 type? Can I add two complex float32s, and does it generate a complex float32? Like, how do I check the validity of that? The base extension can't know because it doesn't know anything about complex. So complex has to be able to kind of tack into that process. So it's very similar to the add-on. It's a similar need to the add-on thing, but it doesn't currently use add-ons to do that. And then, yeah, I mentioned kind service now returns bit vectors. I'd really like that to actually change that to kind IDs at some point because I think they're more flexible. And then the kind service would, I mean, they'll still be bit vectors. It's just they'll be managed internal to the kind service. And you'll have to ask the kind service to compare two IDs. So in summary, wow, sorry, a little bit long. I went through the example IL. I talked about dynamic memory allocation using allocators, and I talked about the dynamic extensibility mechanisms. There are more things, you know, see, I did notice about extensions. I've got that topic there. I probably should go through extensions and talk and show you some examples of what an extension object looks like and how it works. And I think I've showed examples for how to load them, but anyway, I could talk in more detail about the IL debugger, which is still on the floor, but it's getting there. There's the contribution strategy. So how does this get into OMR, et cetera? And then I guess I could talk about anything else people are interested too, if there's other questions that have come about. I guess I'll probably have to start the third one of these with does anybody have any questions that they didn't get time to ask in the last talk because I talked too long?
Yeah. Right. Thanks, Mark. Unfortunately, we're a little bit over, and I know that some of us have to move on to other things, but I really appreciate you taking us through that, Mark. And any questions can go into the Slack channel, actually, so by all means.
Yeah, that's a great idea, too. In the JitBuilder Slack channel and the OMR instance would be perfect.
Okay, all right. Well, thanks everyone for attending today, and next one is scheduled in 2 weeks, and we'll see if we have a topic for that one. All right, thanks everyone. Bye.
Bye.